Hello, dear colleagues. I'm Vladimir Khomenko from Dnipro University of Technology. Today, I will discuss an important but often overlooked issue, the legal and ethical challenges of autonomous drilling control systems working on critical energy infrastructure. Artificial intelligence can greatly improve drilling performance. However, today's liability rules, transparency requirements, and regulations were created for humans, not for machines, making sub-second decisions with irreversible subsurface consequences. If we do not solve these problems now, we may face uninsured environmental disasters and emergency regulations introduced only after serious accidents. Modern autonomous drilling control systems have developed from simple pipe rotation controllers into fully autonomous systems that change drilling parameters in real time without human intervention. They combine downhole telemetry, surface sensors, and machine learning to optimize wet on beat, rotational speed, and drilling trajectory. The advantages are clear. Field studies report drilling that is 50-30% faster, less downtime, and lower human exposure to hazardous environments. However, these same advantages also create new legal and ethical challenges. Drilling rigs are part of critical infrastructure. A single failure may cause environmental disasters, uncontrolled hydrocarbon releases, asset losses worth hundreds of millions of dollars, or fatalities. Unlike autonomous vehicles, drilling artificial intelligence works in an uncertain subsurface environment. Feedback is delayed. It may take hours before a wrong decision becomes visible, and my actions cannot be reversed. These issues are closely connected with the conference topics: ethical artificial intelligence, real-time control systems, and critical infrastructure resilience. Similar problems also appear in artificial intelligence-based mine drainage and smart grid systems. Our main conclusion is simple. Current legal and ethical frameworks are not ready for autonomous drilling. Existing liability rules assume that a human controls every important decision. Transparency requirements assume that every decision can be reconstructed after an accident. Critical infrastructure regulations require a competent person in control, but do not explain what this means when artificial intelligence makes decisions every fraction of a second. We focus on three connected issues: liability, transparency versus trade secrecy, and conflict with current regulation. Together, this creates a serious legal gray zone. Consider this example. An autonomous drilling control system misinterprets formation pressure data and causes a blowout. Who is responsible? The operator for pure supervision, the vendor because of an algorithm error, the data provider because of incorrect sensor data. Current law gives no clear answer. Another problem is whether autonomous drilling control systems should legally be treated as a product or as a service. This decision changes who is liable and under which legal rules. In addition, existing drilling contracts assume a human driller. They usually contain no clauses for autonomous operation or algorithmic risks. The second challenge is transparency. Many autonomous drilling control systems use deep reinforcement learning. These systems make effective decisions, but often cannot explain them. If a regulator asks why the artificial intelligence drilled through a predicted loss zone instead of setting a cosine shoe, the system might not may not provide a clear explanation. However, operators of critical infrastructure must prove that their decisions were reasonable. At the same time, vendors protect their model as a trade secret, including training data, architectures, and model parameters. This creates a conflict. If a driven artificial intelligence cannot be inspected, regulators may treat it as an uncontrolled hazard. The third group of problems concern regulatory compliance. First is cybersecurity. Autonomous systems create many opportunities for cyber attacks. Attackers may manipulate sensor data or influence the artificial intelligence learning process. Existing standards, such as IEC 62443, were developed for deterministic systems, not for learning artificial intelligence. Second is real-time performance. Diligent control requires responses within milliseconds. Plugin increases storage and processing time, making fast response more difficult. Operators a difficult choice. Enable full login and reduce performance. Disable login and violate regulation. This is human oversight. Most regulations require a competent person is in control. But what does control mean if the artificial intelligence makes decisions every 200 milliseconds? Current regulations do not answer this question. This problem can be described simply. When login takes too much processing time, the operator has only two bad options. Either enable full login and risk slower system response, or reduce login and become non-compliant. This is not only a technical issue, it is also a legal problem. If full login is required but disabled, the operator violates regulation. If login is enabled and the system reacts too slowly, the operator may still be liable for the accident. This is a clear regulatory gap. Our first proposal is a three-party liability framework. The operator remains responsible for safe operations and fail-safe supervision. The artificial intelligence vendor is responsible for training data quality and algorithm stability. The integrator, who connects artificial intelligence with the Julian control system, is responsible for sensor integrity and human-artificial intelligence interaction. The key idea is rebuttable presumption of operator control. If the artificial intelligence works inside its certified operational design domain, ODD, liability is mainly assigned to the vendor or integrator. If it operates outside the operational design domain, responsibility shifts to the operator who should have intervened. This approach gives insurers and courts much clearer guidance. The figure on this slide shows how the framework works. Inside the certified operational design domain, liability is generally assigned to the vendor or integrator. The operator may challenge this by proving inadequate supervision. Outside the operational design domain, liability shifts to the operator because the autonomous mode should not have continued. The vendor may challenge this by proving that the system issued proper warnings. For insurance, traditional well-controlled policies are no longer enough. They recommend mandatory algorithmic error and omission insurance for the artificial intelligence vendor with the premiums based on training data diversity and regular offline audits. To improve transparency, we propose a login system similar to the aircraft flight recorder, a drillable black box. For every control cycle, it records input data, the selected action, alternative actions, confidence scores, risks estimates, and any human override. These records should be accepted as a legal evidence and always be available for regulatory inspection. At the same time, storing every control cycle for weeks would create petabytes of data. Therefore, we recommended selective storage. The system continuously keeps the last 60 seconds in memory and permanently saves data only after important events such as pressure spikes, formation changes, human intervention, or confidence reduction. This provides both transparency and practical data management. Our comparison with existing regulations shows several important gaps. Current standards includes API RP 98 do not define operational design domain for artificial intelligence systems, not require artificial intelligence decision logging, and do not require regular independent audits. We propose three changes. First, every autonomous drilling control system should have a formally documented operational design domain. Second, independent reverse engineering audits should be performed at least every 6 months. Third, the industry should create a certification system for drilling artificial intelligence similar to aviation's DO 178C, covering training data quality, simulator accuracy, and closed-loop testing. Legal compliance alone is not enough. Deployment should also follow four ethical principles. Beneficence means reducing health, safety, and environmental risks without harming communities. Non-maleficence means the artificial intelligence must be proven safer than a human driller. Autonomy requires continuous human authority to override the artificial intelligence, including a physical emergency stop button with less than 500 milliseconds delay. Justice means risks must not be transferred to nearby communities or groundwater resources. These principles can also be included directly in the artificial intelligence reward function. These recommendations are practical. Operators should not deploy autonomous drilling control systems without vendor liability, clauses, and independent algorithms audits. Regulators should update standards such as API RP 98 and clarify the artificial intelligence requirements before a major accident occurs. Artificial intelligence vendors should prepare for mandatory errors and emissions insurance and documents the origin of their training data. Legal professionals should develop contracts for autonomous drilling. Insurers should create products covering algorithmic liability. The main message is simple. Action should come before, not after the first autonomous drilling disaster. In conclusion, we present four main contributions. First, a three-party liability model based on the operational design domain. Second, a transparency mechanism using the drillable black box. Third, a roadmap updating current regulation. And fourth, an ethical framework for safe deployment. Future work should focus on measuring the impact of transparency requirements on drilling performance, developing certification standards for drilling artificial intelligence, creating benchmark tests for difficult subsurface conditions, and integrating future cybersecurity framework. Much has been written about autonomous vehicles and aviation artificial intelligence. However, autonomous drilling is fundamentally different because it combines subsurface uncertainty, delayed feedback, and irreversible consequences. For this reason, proactive regulation is essential before a major autonomous drilling accident leads to rushed and ineffective legal changes. Thank you for your attention.